Okay, welcome back. I feel like a TV talk show host or something, so we are back from the commercial break. So let's see. So we just saw something about the complexity of decoding, and we showed it's just like the encoding, it's also n log n. It's also as expensive as taking a Fourier transform, a fast Fourier transform. So it's fairly cheap. Maybe I should do one of two things. One is to show you that the kappa of delta that lower bounded the difference between mutual informations, or we can go into something about the error probability analysis. Perhaps the second one is more interesting at this moment. We'll come back to the kappa of delta later on. But there's a promise to be made, so I have to push this thing on the stack, and then we should remember that I should prove you that at some moment or the other. But let's take a look at the error probability. So to a given channel W, a binary input channel W, I'm going to associate a few parameters. One of them, we already saw the mutual information. So let's say given from W, we're going to define two things. So given W, we will define the mutual information which corresponds to W. This is the W is a channel between X and Y. This is I of XY when X is distributed with a Bernoulli half. Okay, so B half means that fair coin flip is the input to the channel. Okay, so this is, if you expand what this thing means. Okay, this is if I do a complete expansion. I summation over all y with W of y being this is the usual mutual information formula. You sum over all inputs and the outputs. The summation of input is done inside the summation already. Px, the probability of the input, is always half regardless of 0 or 1. You put your W of y given x, log of the W of y given x divided by the output distribution. And output distribution is what is imposed by the input distribution half-half at the output. A given y can be received by either sending 0, okay, or sending 1. Okay? So if 1 is sent, this has probability half. If 1 is sent, you get a y with this probability and so forth. Okay? You can also write it in the form of the h of x, which is 1, minus the h of the x given y. Okay? So this we can also compute as being 1 minus summation over all y. This conditional entropy is going to be computed by what is the probability of particular y, and then I have to put here the what is the h of the x given that y is a particular y. Okay? And this one here, you have to figure out what is the distribution of the x given that y is a particular value y. For this one, so x is distributed, it's a binary random variable. To compute x is equal to 0 is sufficient. And this you'll find as being let's say x is equal to 0 given y is equal to y by the rule of the conditional probability is equal to half W of y given 0. This is the joint probability that x is equal to 0 and y is equal to a particular value y divided by the same number which was occurring here, W of y there. So the halves cancel. Okay, we get like this. Let me define this thing to be W of 0 given y. Okay? So given this W, I can invert from W of y given. From W statistics, I can compute from a statistic of y given x, I can compute x given y once I tell you that x is uniformly distributed. Okay? So this number here is nothing but the binary entropy function, because x is a binary random variable taking 0 with this much probability, 1 with the complementary probability, h2 of this quantity here. Okay? And this h2 of p is simply our p log 1 over p. This is what I mean by h2. It is the binary entropy function. It's the one that looks like a, you know what it looks like. Okay? So H2 looks like this. Okay, all right. So that's the mutual information that we have. This is what we have been working on until now. Okay. All right. The error quantity.
One question, not related
yes.
to what you're saying.
Please.
I don't like people using small h for binary entropy because it's confused. Why can't people just? I mean, most of the books uses
True.
small. Why can't they just use capital H and put a subscript 2?
I have no problem with that. So
I see most of the places, like even Jim Massey's note, you see H, he writes small.
I think that the distinction that I want to make is the following. I think they want to feed to capital H a random variable as an argument. And to the small h's, they want to feed numbers. So the argument of the small h is a numerical value. Argument to a capital H is a random variable. In fact, I find this thing reasonably confusing for the following reason. So this, the capital H is not a function of the random variable x itself. It's a function of its distribution. So it's like the operator E. The expectation of an x, it takes a random variable, values together with the distribution, and computes a numerical value for you. H is the same kind of stuff. Okay? So when you talk about H of the f of x and so forth, I mean, one gets confused as to but f of x is a random variable. It's a function of x, capital X. If I write here, for example, suppose x was a random variable taking values between 0 and 1. Okay, so then, or maybe not, let's call it x, but let me call it to be, let's say, random variable z. Okay, then h2 of z is a random variable, whereas the h of z is a numerical value. These at the end ends up being rather confusing. So, but as far as I can understand, no matter what notation you choose, there is going to be some confusion at some moment. So it's I rather stick to the things which are in the books than inventing new stuff and then creating further confusion. So at least we have one kind of confusion, not two kinds of confusion. So I'll stick to the small h for the purposes of consistency with literature. Some other people, for example, if you take a look at Gallagher's book, he will use a script h, a capital one, to denote the little h2. He'll write something like h of p to denote the binary entropy function. Maybe that's what I should do. All right. Okay, so we have this here. Something else I could associate with the channel is the following thing. I could define a PE. This is the error probability of the channel. This is to say the following thing. Suppose I send a binary x uniformly across the channel. I receive a y. On the basis of this y, I decide whether the x was 0 or not, and I compute the probability of error. Okay? All right. So now, what is this? This is the following thing. So if probability half, you will send a 0. Okay. If this happens, you will receive a y with probability w of y given a 0. Okay. And then you make an error only if w of y given 1 is more than or equal to W of y given 0. Okay. I guess I should put here. Let's suppose a decision was to say that in the equality case, I decide 1. Okay. So, and then or I can send a 1. I receive y's with this 1, but I make an error only in the cases when W of y given 0 is bigger than W of y given 1. Okay. So this is a description of the probability of error. So now I can write this in the following way. I can write this in the following way. I can put everything, all the y's in here. Okay. So now you see in each y, it's either of this type or of this type. But in either case, I'm taking the smaller of these two values inside the summation. In this case, I'm taking the smaller. In this case, I'm taking the smaller. So I can put here the minimum between W of y given 0 and W of y given 1. Okay, good. Okay, fine. So this is the error probability associated with this channel. If the channel W is very good, then the P is going to be very small. If the channel is very bad, for example, bad in the sense that the W of y given 0 is the same as W of y given 1, so the y is independently of what is the input is being chosen, then this minimum is the same as, let's say, the left one. But the left one is a distribution sums to 1. Okay? So this number is going to be 1, and the error probability is going to be 1/2, okay? Which is in fact what you would get by making a decision based on you flip a coin, you decide, you're right half the time, you're wrong half the time, so you can make decisions randomly. Okay? All right, we have that. All right. And for good channels, a very good channel, a given y is either going to come from 0 or from 1, but not from both. So the one of these numbers is going to be 0. So you're summing a whole bunch of zeros, you get a 0. Error probability is 0. So good channels, this number is 0. Bad channels, this number is half. At the same time, note the following thing. The minimum is always less than the any kind of mean. Okay? So if I put here the average of these two numbers instead of the minimum, I get upper bound to this guy. But a better choice is the geometric mean. Okay? The geometric mean is also bigger than the minimum. Okay? So this is less than half summation y, the square root of W of y given 0 and W of y given 1. Okay? Because the geometric mean is always bigger than the smaller, okay? Because each of these numbers is bigger than the minimum of these two. So the product is bigger than the square of the minimum. Square root of the product is bigger than the minimum itself. So this is a upper bound. Okay? And this quantity here has a name. Okay? I'll call it to be Z of W, following Arikan's notation. Okay? And the Z of W is known as the Bhattacharya parameter. So ZW is known as a name. This object is known as the okay. So one thing about this ZW is the following thing. Again, if the channel is perfect, namely if one of these two numbers is certain to be 0, y can come from either one or the other of these zeros and ones, but not from both. In this case, again, the Z of W is 0. Okay. And if the W is a terrible channel, W of y given 0 is the same as W of y given 1. In this case, this product is the same as W of y given 0, let's say, the square root. So you sum, you again get 1, so again get 1/2. So it is not a bad bound. And indeed, if you use the Cauchy-Schwarz inequality, the summation of a product is less than the L2 norms of the two things. And the L2 norm of, if you square this quantity here, you get W of y given 0, you sum it, you get 1, you do this one, you get 1. So the Z of W is always between 0 and 1. Okay, so the Z of W is never, will give you something which is more than 1. So this bound on the error probably is never going to exceed half. So it is always a decent bound. Okay? Indeed, what you can show is that if you were a bit more clever, I could have turned this thing around and then show you that the Bhattacharya parameter squared divided by half is a lower bound on the error probability. So the Bhattacharya parameter is a reasonable estimate of the error probability itself, and is an easier quantity to work with analytically, because a min is an ugly function to do analytics on, okay? Whereas a square root is not too bad. Okay? So there's an advantage of working with Bhattacharya parameters as opposed to directly with the error probability itself. Okay? So I'll take the Bhattacharya parameter as a proxy for the error probability, and I'll try to estimate what does polarization do. I'll try to analyze what does to this Bhattacharya parameter z, and then to analyze the effect on the error probability via the Bhattacharya parameter. Okay? All right. Good. I'm not sure if any examples are needed. For example, for the binary erasure channels, okay. Let's copy to ZW for the BEC, just in case. If we have this channel here with this, so this in the summation, the y is equal to 0 contributes nothing to the Bhattacharya parameter, because the transition from 1 to this y is 0, so one of these numbers is 0. This one contributes also nothing to the Bhattacharya sum. Okay? Only contribution is coming from the y is equal to question mark, in which case this number is p, this number is p, get p squared, squared is also p, you sum, so the z of this channel, z of a BEC, p, is p. So for erasure channels, the Bhattacharya parameter is nothing but the erasure probability. Good. In which case, in fact, the bound is tight, because you see that in a channel like this, if you receive 0 or 1, you make no errors anyway. If you receive a question mark, you have to flip a coin to make your decision. So with probability p, you get an erasure. With half, you make an error. So p over 2 is exactly error probability, and this bound here gives you exactly the correct thing anyway. Okay. For the BSC, okay, with crossover probability p, if you take a look at this 0 here, this is 1 minus p, this is p. You take the product, p times 1 minus p, take the square root. Okay. This one has the same contribution, p times 1 minus p square root. So the z of a BSC with crossover probability p is twice the square root of p times 1 minus p, which is, let's say, the square root of 4p 1 minus p. This is a number between 0 and 1. Okay, so the square root. Okay, it is 1 when p is equal to a half. So if you have a terrible channel, you get again the bad bound. P is equal to 0 and 1 gives you correct things. In this particular case, of course, this overestimates the error probability quite a bit. Okay, in this case, the estimation of the error probability is bad, because here you would simply, if p is less than a half, okay, let's say, you will decide on whatever you received, okay, and your error probability would be p, okay, and p is typically is much more than this guy, especially with the square root operation. You're blowing up p by quite a bit. Okay, but all right. So if p was 10 to the minus 6, this will give you something like 10 to the minus 3. So you blow up the error probability by quite a bit. Okay, good. But now we have this concept here. So we also have, we'll define, I'll worry about this quantity here and this quantity here. I will ignore the PE because I have good bounds on PE in terms of the Z. So from this point on, I'll ignore the PE, work only with these Z's. Let me rewrite this thing. So that, okay. And we have ZW. I will write in the following way, if you don't mind. The ZW was equal to my given one. I'll write in the following way. Every so often it might be useful. y. Okay. But then note the following thing. This was exactly w of 0 given y. This is exactly how we had computed the w of 0 given y. So there's a factor of 2, okay, there in this. Okay. So this is exactly 2 times w of 0 given y was like that. Okay, remember how we computed w of 0 given y? This was, we had half w of y given 0 divided by w of y. And for w of y, I wrote down the half w of y given 0, half w of y. I cancel the halves, but before we cancel the halves, it was like this. So this quantity, if you put the 2 to this side, you get this ratio as this. And similarly, this thing is just 1 minus the w of 0 given y times 2. So this is twice 1 minus w of 0 given y. Okay. So the z of w is summation w of y square root of 4 times w of 0 given y 1 minus w of 0 given y. I could have written here w1 given y, same thing, but the reason I wrote it in this form is the following. I want to get these two to look similar. So there's a summation over y and some distribution on the y's. This w of y is a probability distribution. I have the same object here. So this thing is a expectation operator, a summation over all values, the probability of this value times something which depends on the value. Same thing here. And with the same function, a function of the same object, this w of y given 0, it appears on both sides. Okay? Okay. So if I call, for example, this quantity to be a function of y, okay, so think of the y being a random variable with this distribution here. Okay? So then what I have is the following. What I have here is that what we have expressed is that this I of w is an expectation of 1 minus h2 of some random variable. Let me call this random variable capital delta for the time being. So delta is a random variable which is a function of the distribution y. So y has distribution w. Okay. This function of y is simply f of y is w of 0 given y, and the y and the probability that y is equal to y is the w of y, which is half. So I have this w of y which I wrote down already, just copying here for, because I erase, you don't. You have your notes, I don't have it here. So this is that. And the z of w is the expectation of square root of 4 times delta times 1 minus delta. Okay. So I have two quantities. They're both expectations of one function or the other function of the same random variable delta. Okay. So in particular, the following is true. If I plot the following plot, I will do here on, let's say, the x-axis, I'll put 1 minus h2 of delta here. On the y-axis, I put 4 delta 1 minus delta on the y-axis. Okay. And I'm going to have very little delta between 0 and 1. Okay. At delta is equal to 0, what do I get? At delta is equal to 0, this number is 0 on the y-axis. X-axis, the h2, remember, is like this. So at delta is equal to 0, I evaluate this thing to 0. So 1 minus that is here. So I start from 1. Okay, maybe I should put this. Okay. By the way, these two functions are symmetric in delta across 1/2. So if I replace delta by 1 minus delta, this doesn't change. Okay. If I replace delta by 1 minus delta, The binary entropy function is also symmetric through the middle line 1/2, so it's switching delta to 1 minus, it does not change that either. So I can make this plot only going from delta going from 0 to 1/2, and then from 1/2 to 1 is going to just trace the curve backwards. Okay? So if I do that, what I'll find is the following thing. At delta is equal to half, this number is 4 times half, which is 1. Okay? And this number is h2 of half is 1. 1 minus 1 is 0. So I end up in this point here. Okay? So this is at delta is equal to 0, I'm here. Delta is equal to half, I'm there. And I go back, and whatever curve that I do. Okay? But perhaps we should just do this thing, computation, so that we see what this look like. Okay? Let me define. So I'll define the binary entropy function h of p as being p log p plus 1 minus p times log 1 minus p, except I need a minus sign. And let me also divide by log 2 so that we are in the log base 2 computation, so I don't get ln2s and so on and so forth to confuse us. Okay. And what I'm supposed to plot is the following thing. So I need to put a parametric plot with the range of x to be between 0 and 1. The range of the y-axis to be in 0 and 1. And it says that the dummy variable is t, so I'm supposed to use t as an argument to the x and the y functions. So t range is supposed to be 0 to 0.5 is sufficient, we said. Okay. And I'm supposed to plot, on the x-axis, I'm supposed to plot 1 minus the h of this parametric variable t. On the y-axis, I'm supposed to plot square root of 4 times t times 1 minus t. Okay. How come I get this terrible looking object? I guess it did not cover all the way to 0.5. Let me make this range to be 0, 1. It got even worse. Okay. How irritating. So this GNU plot must be plotting only a bunch of points in here. Okay. And sorry? This should not be symmetric because I'm not plotting the h of t itself. I'm plotting the h of t versus the square root of the t times 1 minus t. What I'm actually reading is the following thing. Instead of falling in here, okay, it's, I think, not evaluating these points there. I should have tested this thing on the computer before. Okay. How can I make sure that the GNU plot plots a sufficiently finely spaced t? Okay, let me do the following first. Let me also try this one. Okay, now we're better. Apparently there's difficulty evaluating p log p when p is 0. Okay, so I suspect that there was some error there. So let me make this thing to be, in that case, something like this. I can probably give this one to be 0.5. Anyway, so now that you see that this is a curve from here to here. So you remember this shape? Because I want to just plot it by hand again. So this is a curve which was essentially like this, right? Something like this was the possibilities there. Okay. So now remember what we were doing. So this is simply plotting 1 minus h of delta across the square root of 4 delta 1 minus delta as just a function of delta as being a completely real random variable. What we're doing here is essentially taking suppose the values of y, suppose there are 10 different y's, okay? So for each of these y's, I get a point on this thing, okay? The value of this delta of y evaluated once through this and once like that. And then I'm weighing these numbers by the probabilities that are associated with that particular y and combining them. So what I'm doing is I'm computing a convex hull of points on this curve. Okay? So any iz value is going to lie in the shaded area here. Okay? I need to take the convex hull of this particular curve on 2D. Okay? You find the smallest convex set which contains this arc, okay? And any IZ value, okay, is going to remain inside this thing here, because by taking weighted convex combinations of points which lie on this curve, you cannot go outside this convex hull. Okay? Is this clear what I'm saying? Of course. So let me actually describe this thing in a slightly different way. Suppose I give you a set of points, like this one. Okay? And then I say, you're allowed to construct additional points in the following way. You can pick here as many points as you want inside this given set. And then you can weigh them by numbers which add to 1. And you take the vector sum of these 5 points, let's say, with 5 weights which are summing to 1, and they're all positive. If you do that, you're going to find a number which is inside the envelope of these things here. There's no way to escape this rubber band that I put around these 5 points. Okay? If I do this for all possible points and all possible weights that I can take which sum to 1 that are positive, you end up with essentially closing this thing to a convex body. If this original thing had various dents and so forth, they will be closed up by this procedure. In this particular case, a particularly simple set. The set is just a line in 2D. If I do this, I'll simply will close the gaps between these things and I'll obtain this particular curve. Okay? I'm glad you asked, because it's one of these things in which people are confused about this. But whenever you have, let's say, 3 quantities, each expresses expectations of some function of the same random variable, then these 3 objects are going to lie in some convex body, which is the convex hull of the thing which is traced by singular distributions. Okay? So let me tell you one more thing. Suppose you have suppose you had few quantities. Let's say quantity 1, quantity 2, quantity 3, and suppose each of them were expressed as expectation of some function of a random variable. Let's say it is x, this random variable. Quantity 2 is expressed as maybe some other function, but of the same random variable, x. And the quantity 3 is also expressed as maybe some different function, but of the same random variable x. If you have these 3 quantities here, then the possible values, joint values of q1, q2, q3 is going to lie in the following convex hull. You compute in 3 dimensions the curve f1 of little x, f2 of little x, f3 of little x, where x runs through its space of values. Suppose x is, let's say, 1-dimensional, for example, say between 0 and 1. So a parametric curve in 3 dimensions given by the pair f1 of x, f2 of x, f3 of little x, okay? And then you let the x range between over its whole range. This is going to trace you a nice curve like this. And you take the convex hull of this curve. Okay? This q1, q2, q3 is guaranteed to lie in this convex hull by the same argument that we had there. Okay? So because these q's are constructed by taking various points on this line, this curve that we had, and then taking a convex combination of this by the weights that are given to these little x's by the expectation operator. Okay? All right. So so consequently, we have the following nice relationships between the z and the I. For example, the z plus I is always bigger than 1. Okay? So you cannot find a channel for which the z plus I is less than 1 is impossible, because the only possible zi values are above here. Okay? And the zi cannot be too far away from this either. Okay? So this is, you cannot get any zi's which are outside of this upper envelope either. But the nice thing about this diagram is the following. It says this. In particular, looking at this diagram here, if, let's say, I of w is close to 0, Suppose I say that I gave you a channel whose mutual information is somewhere close to here. So now I can put these things to be I of W and the Z of W here. Okay? So those are, any possible channel is going to have an IZ pair which is inside this shaded region, cannot be anywhere else. Now I tell you that I have a channel W, I don't tell you what channel it is, but I tell you that its mutual information is somewhere around here. Okay? It's close to 0. Then a Z must be something close to 1. Okay? Okay? If I told you that I gave you a channel whose Z is close to 1, Z is around here, then its I must be close to 0. Okay? So this in fact goes both ways. Okay? Also, if I told you I have a channel for which I of W is close to 1, I have a channel whose I is here, then its Z cannot be too big. It has to also be close to 0. Okay? Then Z of W is close to 0. And conversely, if I give you a channel whose Z is close to 0, its I must be close to 1. Okay? So the I and the Z are completely complementary. If you have a channel with large I, it must have small z. If you have a channel with small z, it must have large I. Large z must be small I, blah, blah, blah. Okay, so all 4 implications, either vice versa.
I of W is equal to 1 probably means that Y doesn't have any sort of randomness and therefore the variance should be 0.
Absolutely. You're completely right. So this is completely intuitive. However, what is not intuitive is the following. These approximations are not independent of W itself. Okay, so if I tell you that regardless of the output alphabet size, regardless of how complicated the channel is, I can call uniform bounds. If I say that I have a channel, I don't tell you how complicated the channel might be, whose mutual information is less than 0.01. You know for sure that its channel Z must be bigger than 1 minus whatever, so some value which depends only on the 0.01, but no longer on the channel itself. So estimates of this I and the Z are now uniformly across all possible channels. So regardless of the channel, if you know something about the value I, you know something about the value Z, and vice versa. Okay. So I don't want these things to depend on the particularities of the channel itself. If I showed you something about only for the BEC or the BSC, okay, maybe this relationship is true with these estimates. Okay. But this is saying I have estimates which are uniformly good across all possible channels, without knowing anything about the channel itself except for being binary input. Otherwise, the fact that for any given channel family, suppose I told you that my channel is a BSC, then okay, these things have to happen is okay. But essentially I should have said that I can find functions of epsilon, okay, so that the IW less than epsilon guarantees that the ZW is more than 1 minus f of epsilon, okay, and IW more than 1 minus f of epsilon. Epsilon guarantees that a ZW is less than epsilon, and so forth. Okay, and these Fs, they are universal. They depend only on the epsilon and not on the channel family or anything else. I may be saying too many things about this particular point, but the reason I want to this becomes important is the following: if you fix the output alphabet, if you said that my output alphabet is, let's say, ternary, okay, then you can convert any kind of statement about one particular channel into a whole family because the set of channels then becomes compact. Only 3 numbers will describe all channels because you only need to tell me what is the Y given, Y can take on 3 values. You tell me Y given 0 given Y, 1 given Y, etc. for only 3 values. That's a nice compact space, so any estimate that you have is going to be guaranteed to there. But the problem is that as we do this polarization process, you create channels with alphabets which are bigger and bigger at the output. So end up with problems of my estimates, are they getting imprecise at some moment or not, becomes important. So I have to have estimates which are uniform regardless of the output alphabet size. That's the reason why we worry about this. Okay, now secondly, what I want to discuss is the following thing. What does polarization do to Z? So we saw that we have some idea as to what polarization does to I. Okay? We need to know something also about what does it do to Z also. Okay? So given a channel, so let's see, so proposition maybe, or lemma. So in terms of the ZW itself, what happens to the Z of the W plus and W minus? It turns out the following is true. You would expect that the Z of the minus channel should be worse than the Z of the original channel itself, because minus is a worse channel than W, so its error probability you expect to be worse, and the Z parameter maybe is also worse too. Okay, but the point is that it's not too much worse. Okay, so the Z of the W minus is worse, but is at most, the Z parameter is at most doubled. Okay, so things might get worse, but they don't get too terribly worse. However, the W plus, you expect it to be better. You expect that the Z parameter should improve. It should get smaller. Error probability is smaller. Okay. Indeed, it is better, and in fact, exactly equal to ZW squared. Okay. Squaring is a much more powerful operation than halving. Okay. So if you think of the W minus as being doubling, its counterpart you might expect to be maybe halving. Okay, so minus does something, and the plus does something better. On the average, maybe they are doing the same thing. But this is doing much better. If you end up with a ZW, which is already good, suppose 10 to the minus 3, at the plus side, you're getting a much better channel with error probability 10 to the minus 6. Okay, so one operation will get you the error probability down a lot. Okay, and this one is, the minus one you create is not going to be too terrible. It's not, if it is 10 to the minus 3, it's going to be 2 times 10 to the minus 3. If this was square root instead of 2, so that's a, square root is a much more irritating operation at the low values. Okay, so if you take the square root of a small number, you are much more than doubling it. Right? If you have 10 to the minus 6, you take its square root, you multiply by 1,000, right, and not multiply by 2. If this upper bound had been square root, we would be in deep trouble. Polarization would not take place. Okay, you would not get good things. But since the squaring is so much stronger than the doubling, this will tell us that the good channels are getting really good. We'll see how this will work out in some amount of time. It might take us the whole afternoon to do this, but we'll show that the difference in the balance of these two powers, squaring, which is good, doubling, which is bad, okay, but the good is so much better than the bad, is going to help us show that the polarization happens sufficiently strongly that we can get strong estimates on the error probability is going to be coming from here. Okay. Now, and the proof of these are simple. So let's see. Let's look at the W plus. Maybe it's easier. Okay. So or W minus. What the heck? Okay. I'm supposed to go over all outputs of W minus. W minus was a channel from U1 to Y1, Y2, so I'm supposed to sum over all of these things. I'm supposed to put here the square root of W minus or Y1, Y2 given 0 times W minus or Y1, Y2 given 1, and take its square root. Okay. So this guy, Y1, Y2, I should now expand these two things. Okay. So this W minus of Y1, Y2 given 0 was given by W of Y1 given 0, Y2 given 0, and the corresponding things with the 1 1s divided by 2. And in here I had the W of Y1 given 0, Y2 given 1, together with the Y1 given 1, Y2 given 0. Fine, okay, so I have some ugly expression in here. I get, I guess, a half which comes out or something. These 2's, I'll take that out of the square root as being just one of them. Inside the square root, I have 4 terms. Okay, this times this times that times that, and so on and so forth. Okay? All right. Let's take a look as to what these things are. Let's take a look at one of these terms. y1 given 0 squared. Okay? And then I have here the y2 given 0, y2 given 1. This is the term which comes from multiplying this term and this. Y2 given 0. Okay? And then I have 4 terms which are similar. For example, let's take a look at the second term. This times that. Okay? And then I have here W y2 given 0 squared y1 given 1. Let me write down everything. Okay, at least now that I've done half, I might as well just go through the whole thing. And then we have this times this. Given 1. These are all inside the square root. And the last thing is this times that. Y2 given 1. Okay. Okay. So now observe the following thing. If we take a look at square root of, actually let me just show it for this. This is less than square root of A, square root of B. Whenever you have non-negative AB, this is the case. Why? Square each side. Okay. On this side you get A plus B. Here you get A plus B and then the cross term. Okay. So the cross term is non-negative, so okay. Right-hand side is bigger than left-hand side. It's shown by simply squaring both sides. You have only A plus B on this side. You have square root of this plus the square root of that plus something more. Okay? So clearly this is Adams. And same thing, if you just do it for ABC or ABCD, you get that. So consequently, this guy is bigger than taking each of these square roots separately. Okay? You can upper bound the square root of a sum by sum of the square roots. Okay? So now we are very nice. Take a look at each term separately. Each of them are going to be the same, so I'll just take a look at one of them. Take a look at this term here. This square comes out, so the first term. Okay. Y1 and Y2, we have, what do we have? We have Y1 given 0, square root of Y2 given 1. Okay. So now this summation is a double sum, but the first term depends only on Y1, so I can simply, the first term here is equal to a summation of Y1, summation of Y2, this thing. Now this quantity, you're simply computing Z of W because you're going through all outputs of W indexed by Y2. Okay. And you compute the square root of the probability of this output given 0 times the probability given 1. This is ZW. Okay. It's a constant in this sum because it doesn't depend on Y1 comes out. And this summation sums to 1 because you're summing the conditional probability of Y1 under a fixed input. So this is equal to Z of W. Okay. All right. Fine. So now this part contributes ZW. It's exactly the same, okay, except the rows of the Y2 and Y1 are swapped. Okay. You get ZW again from this guy. Same thing on the third term. You get ZW from the third term. Fourth term also. Okay. So this whole thing is less than, there is a half here, but there are 4 terms. So 2 times ZW, because each of these 4 terms, they contribute ZW. You get 4W but there was a half in the front. So, okay, you get 2ZW. So we have shown this one, okay? This is even easier because equalities are always easier to prove than inequalities, okay? So we had to use some clever trick to say that the square root of a sum is less than the sum of the square roots. For the W plus, there's no need for such a trick, and then we'll do it when we come back. It'll be a easy ramp up to the next lecture, so we'll see these things, okay? All right. And that point on, we'll do something more complicated to show that the polarization is fast. It should happen, I think, before the end of today. All right.
This is the reason why we end up with more good channels and less bad channels.
No. The reason is the following. So if the number of good and the bad channels depends only on the original channel's IW. If the original W itself, the base channel that you're polarizing, if that had mutual information, let's say 0.03, okay, then at the end you end up with 3% good channels, 97% bad channels. So the fraction of good and the bad channels depends only on IW itself. Okay. So the example of the 70%, 30% was like that because we had a channel whose IW was exactly 0.7. So the 0.7 was the 70% giving the good channels, and the complement 30%, 0.3 was giving the fraction of bad channels. So how many good channels and how many bad channels you have are determined purely by the original channel's I of W. This one will show us that the good channels, when they're good, they're very good. Okay? So this says only about how good the good channels are. It won't tell us anything about the number of good channels. It will tell us only anything about the strength of the good channels. Maybe you end up with 3% good channels in the case of this IOW, initial IW being 0.03, will give you only 3%, very few good channels, but the ones who are good, I'm not talking 97% who's terrible, but the 3% good channels are going to be really good channels because they are created by these plus minus things which makes the ZW small, but if ZW is small, it has to be very small because of the squaring property. It takes a bit of getting used to. It's not something, I mean, none of these are trivial stuff. It took me, but Erdal also, I think, quite a while to realize, oh yes, this is what's happening. So I'm telling you things that we discovered by a few weeks of staring at this thing and then so forth. So it's perfectly okay that at the beginning you make wrong hypotheses is perfectly normal. So don't say that, oh, I was wrong. That's not the case. You are right in some deep sense. Sir? Yes. 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 So we haven't proved anything yet. So we have proven the following things. We have shown that the IW polarizes, and based on this diagram that if IW is big, ZW is small, and vice versa, we also know ZW also polarizes. So at the end, you obtain channels W for which the Z is also either close to 0 or 1, and exactly complementary to the I. Okay. This kind of stuff will help us show that the Z's which are good are in fact particularly good. Okay. Because squaring is essentially it's this. So compared to squaring, multiplying 2 is nothing. Okay. So suppose that I could have shown you this, which is obviously false, but okay. I mean, suppose I could have. Okay. Suppose this was the case. If you ignore the first approximation that in a process which either multiplies by 2 or squares, the multiplications by 2 are equal to doing nothing. Suppose you granted me that one. On a typical path which leads from a W to one of the synthetic channels, you're going to have about half plus operations and half minus operations, because that's the dominant way to reach the ith level, is to have I over 2 plus operations and I over 2 minus operations is the great bulk of the channels that you created. But the I over 2 plus operations will square the Z I over 2 times. Okay. So squaring something a whole bunch of times is raising it to the power 2 to the number of squarings. So it will end up with the Z of a typical channel at the ith level. So this S is an I of these plus minus signs with about half of the pluses and half minuses. This is going to be like ZW, the original channel, whatever it is, to the power 2 to the I over 2. So you take this enormous number, okay? Suppose I is 100, okay? Then you have 2 to the 50, okay, in here, okay? And then you're raising ZW to the 2 to the 50th power, okay? That's an enormous thing. And this number, by the way, since 2 to the I was the block length, this is like the square root of the block length. So this is like essentially some number which is less than 1, okay? If the original channel was ZW equal to 1, anyway it's pointless because you have a terrible channel that you started from, you cannot do anything about this. If your original channel, let's say, has Z parameter, let's say P, okay, which was, this was the P is the ZW, then you have P to the root N as the estimate of the error probability of the synthetic channel that you created. So this is saying that the, and this is equal to 2 to the minus root N times a constant. This constant is just the log of the 1 over P, okay? So this is saying that the error probability of the synthetic channels are decaying exponentially in the square root of the block length. Okay? So if you take a look at the, I'm really sorry, I'm taking way too much time than we have. If you take a look at how do random codes behave, if you take a randomly chosen code, that's the Shannon's construction of how to do channels, you will find that the error probability at the end, after a block, is exponential in the block length itself. So this is not as good as random code, because instead of the block length itself, we get square root of the block length. But this is still faster than any kind of polynomial decay. This is 2 to the minus root N is faster than 1 over any polynomial. So this is better than proving that the error probability, like n to the minus 10. Okay, this is much better than that. It's a much faster decay. Consequently, this is saying that these good channels, when they are good, they are very good. The error probability is like exponentially small in the block length of the code that you have created. Okay, but to come to here precisely, we have to do a lot of work. This is a very shaky argument. I ignore this too. Can you really do this, etc. Is of course very doubtful. But to the first approximation, it seems about right. Okay? Indeed, we will show this. Sure.
How do you approximate to ZW finally?
So this is exactly the definition of ZW. Because ZW, remember, is I'm supposed to sum over all the outputs of the channel. So this summation, the inside summation here, depends only on Y2. If I do the summation, I get ZW here. So this thing can come out of the summation because it's a constant. Okay? And the inside sum, you're summing the probability of Y under the 0 input. So the summation is the total of probability is exactly equal to 1. Okay? So if I sum over all the outputs, the P of the Y given any particular input X, I should sum to 1. Okay? So this is ZW times 1 if you want. Okay? Which is equal to ZW. I should have maybe done it like that, would have been more transparent. Okay.